Hello everyone and welcome to BoostBusters Gas Exchange Handbook. And today it's time for the multi-cylinder version of the course or chapter. And in order to keep this course at a decent length in time, some basics are necessary to capture from other courses. That will be thermodynamics, unsteady gas dynamics, a little bit about the internal gas exchange system from the single course, and to have a good guidance where to find other pieces of information. I recommend to have a look in chapter 10, which is the starting point for the courses and which give you information where to find different parts. The main thing in this course is to describe different number of cylinders, cylinder orientation, banks and so on, and also different firing orders. It's also important when multi-cylinder consideration in the gas exchange point of view becomes interesting. There are several engines around with multi-cylinders, but if they are only connected through the crankshaft and not between the air ducting or an exhaust ducting, then you can jump this course because they will behave exactly as the single cylinder counterparts. Another important overall consideration taken into account in this course is when you add charging system to an engine. Charging system can be adopted to single cylinder engines, but most of the time charging systems are combined with multi-cylinder engines. Most multi-cylinder engines join nicely together with turbochargers, but there are some things to keep in mind to make your selection as good as possible. A soft start would be to look on the different types of cylinder numbers you could find around multi-cylinder engines. The simplest and maybe most useful type of engine would be the inline engine. So the inline engine have all the cylinders in one line and only one cylinder head. In one way, it's the simplest and maybe also the cheapest engine to build, but it becomes very long. So installation-wise, in many application cars, motorbikes, it has its limitations. What can be done then is to divide, for instance, this inline 6-cylinder engine into two banks with 3 cylinders, 3 cylinders. Then you obtain something called a V engine. The banks are this cylinder sticking out like that. So V engine have 2 banks, an inline engine have 1 bank. If you have 2 banks, you could have you have a V angle between them, and that V angle could be anything between 45 degrees and up to 180 degrees. There are very special V engines. I know that Ferrari have made such engines which have a 180-degree bank angle. Then they look like this. They are then called false boxer engines because a pure boxer engine always have 180 degrees. But the boxer engine will have pistons sitting on each side of the bank on different crank pins. And where are my hands now? The pistons will operate in this way and create a little bit better of a balance. If you have a false V engine, the pistons will move like that. It's not a problem if you have a Ferrari with 12 cylinders. if the engine is rocking around a little bit. But if it would have been a two-cylinder engine in a motorbike, I wouldn't drive it. Let's start to have a look on the cylinder interactions which can happen in a multi-cylinder engine on exhaust side. Hopefully you have been following the single cylinder course, you are familiar with the physical plane like that. If you look carefully, this physical plane is expanded from the single cylinder course. So beside having the self-induced pressure waves in the cylinder itself, we have new visitors. We have secondary pipe reflections, which are coming from downstream parts of the exhaust system, which could also happen in a single cylinder engine. It could be the secondary pipe presence in itself. It could be catalytic converters and silencers. But even more complicated, we have neighbors. So neighboring cylinders, especially those cylinders which are close to the cylinder in question when it comes to firing order, could send disturbances, pressure waves which was intended to join in the same collector and just transmit out through the secondary pipe. But when you have a compression wave coming from a neighboring cylinder, a fraction of that pressure wave will also go back to the cylinder in question and create disturbances. Looking at the physical plane is good for overall understanding, to have a better picture where different pressure waves comes from. Most of the time we don't have that luxury in a going engine. What we do have is either simulated or measured pressure traces. Pressure traces is taken from a pressure transducer, normally as close to the engine or the exhaust valve as you can come. And what you will get in return is a picture like this, also showing different influences from other cylinders and the secondary pipe. The first is always the highest amplitude pressure wave which comes from the cylinder where the pressure transducer is mounted. It goes up depending on the length of the exhaust primary pipe. It could take some time if we are lucky. After the valve overlap, the interaction from other cylinders and from the secondary pipe happens. But especially at lower engine speed, where the time to make exhaust port duration is longer, then the disturbances could move into the valve overlap at the end of the exhaust phase, where the engine is very, very sensitive for disturbances and cause problems. And what kind of troubles? Well, from the single cylinder course, we learned that compression waves coming in from the exhaust side will most definitely push exhaust gases into the cylinder, being in the process of gas exchange, and therefore lower the potential for delivery ratio, volumetric efficiency, and also the hot exhaust gases could trigger detonation and abnormal combustion. I'd like to start the exemplification on the three-cylinder inline engine. The three-cylinder inline is an even firing engine. That means that with an even distribution of the pulses, there will be 240 crank angle degrees between each ignition. The nice thing with this is that then it will also be a 240 phase shift between the different cylinders in firing order, opening the exhaust valves. So in order to show that, first we have the picture of the 3-cylinder inline engine, and the firing order could be different on different engines, but in this case we fire cylinder 1, we fire cylinder 3, and we fire cylinder 2. Looking in the gas exchange diagram, where we bring everything together, at the horizontal first axle, we would have cylinder number 1. Since cylinder number 3 is the first cylinder to come after cylinder number 1, the second horizontal axle will represent cylinder number 3. And of course, the last one, cylinder 2, will be on the top. Normally, I say normally, in racing applications, things could be different, but normally we assume that the duration of an exhaust valve is 240 degrees, which means that the duration of one cylinder's exhaust valve is the same as the spacing between two cylinders, which are as close as possible in firing order. On a simplified language, that means that on a 3-cylinder inline engine with even firing, only one cylinder at a time have the exhaust valves open. This is very, very good, because then this engine is completely unable to disturb itself from the exhaust side. Therefore, 3-cylinder groups in general for 4-stroke engines, even firing, is a real advantage. And as you can understand, a 6-cylinder engine could very easily become 2 3-cylinder groups. That's true for inline 6-cylinder engines, it's true for some V6 engines, and it's true for boxer 6-cylinder engine like Porsche, for instance. So take a 6-cylinder boxer engine, for instance, with 2 perfect 3-cylinder groups, identical with this one. No exhaust interaction will happen on that engine as long as the exhaust pipes on each side of the engine does not come into contact with one another. Well, all engines are not 3-cylinder engines. Most of us know that 4-cylinder inline engines are very, very popular. And then the situation changes a little bit, because if you consider this 4-cylinder engine and you try to stack the different cylinders in the diagram in the same way as for the 3-cylinder engine, you understand that also a 4-cylinder engine will have a duration on exhaust valves cams of 240 degrees. But since you are installing 4 cylinders in the total rotation of 720 degrees instead of 3, we need to do the spacing smaller. So the spacing between 2 adjacent cylinders in firing order closest together is only 180 degrees. So with the duration of each exhaust valve of 240 degrees, spacing 180, we have an exhaust overlap of 60 crank angle degrees between the cylinders. So now there is a huge potential for the 4-stroke engine to be communicating between cylinders on the exhaust side, which is basically bad news, because now the cylinder which is in gas exchange and should be left alone could be disturbed by the next cylinder in firing order, opening its exhaust valve, creating high amplitude compression waves, where parts of that will be distributed into the gas exchange cylinders. In a simple way, for 4-cylinder 4-stroke engines, cylinder 1, 2, 3, 4. Cylinder 1 and 4 can be connected to each other, because between those cylinders there is a 360 degree delay. so they don't communicate. That's good news. Also in cylinder group 2 and 3, in between them, there is a gap of 360 degrees, so no crosstalk. The problem starts when you try to connect cylinder group 1, 4 with cylinder 2 and 3. It could be made, but you prefer to have that connection point as far away as possible from the engine. So the longer pipe length you could have to that crossover point, the better for the engine. If it comes close, there will always exist an engine below where these interactions and short circuiting can take place. Not a problem on a 3-cylinder engine, but when you come up to 4 cylinders, that problem becomes apparent. And the more cylinders you stack to the same exhaust collector, the bigger overlap will happen between the exhaust valves and bigger problems with short-circuiting internal EGR. Now let's make this a little bit more complicated. The engines discussed so far have been even firing engines. So between 2 cylinders, which are as close as possible in firing orders, the spacing is the same. But there are several engines around which don't have this luxury. And one example is different 2-cylinder engines. 2-cylinder engines are so far not so common in cars, but you can find them frequently in motorbikes. I will give you some examples. But before I do that, I will also present the diagram you have in front of you, because it's a little bit different from the diagrams you have seen before. Cylinder 1 is represented on the lowest horizontal axle. This is crank angle rotation. Cylinder 2 would be cylinder 2 in an inline 360 degree 2-cylinder engine. 360 degree means that you have 2 parallel pistons which will operate up and down together. And inertia-wise, the feeling in the handlebar, if this is in a motorbike, would be the same as a single-cylinder engine. Pretty vibrating. And old guys like myself, who have been riding Triumph and similar British motorbikes, were used to that kind of behavior. Gas exchange wise, you will get a payoff from all the vibrations, because those engines are very nicely operated gas exchange wise. They are operated like the 2 3-cylinder group in a 4-cylinder engine or the 1 4-cylinder group in a 4-cylinder engine. They don't interact. No existing exhaust valve overlap. Good news. The other firing order which obtains this very nice situation would be the opposed piston engine or the boxer engine. It's also separated 360 degrees. Vibration-wise, a better situation because the pistons inertia, to some extent at least, take out each other. Okay, now the party is over. So we jump to a very popular engine today. It's still a 2-cylinder inline engine, but this time the pistons are not moving like this in parallel, they're moving like that. Vibration-wise, inertia-wise, it's a big step forward. So vibrations are taken care of in a much better way. The problem is that the gas exchange spacing becomes much more uneven, which means that one of the cylinders will be more disturbed by the other cylinder than the other way around. So the engine becomes a little bit limping, and the firing order for a 100-degree inline engine is the worst of them all. Next alternative would be the 90-degree V engine. It's a little bit less uneven, it has about 270 degrees on one of the legs, but still a little bit uneven. Going up to the traditional Harley-Davidson engine, the V engine with a bank angle of 45 degrees, it becomes more symmetrical, but still a little bit uneven. Uneven engines, we will look on that, will have a distribution of the delivery ratio. If you go in and measure volumetric efficiency or delivery ratio on an even firing engine, if you measure it in cylinder 1, 2, 3, 4, I don't say that it always becomes exactly the same, but theoretically it has that potential. But with uneven firing, the situation in different cylinders will be different, and so also the delivery ratio. Here we have the 4 different two-cylinder engines, and we also have the delivery ratio distributed for the different cylinders. So for the 360-degree engine, and it should also be stated boxer engine here, you cannot tell the difference. They are completely similar. Taking the step to the 180-degree engine, you can see here we have differences at about 5% or something. On the V90-degree engine, things becomes better, and on the 45-degree V engine, also a little bit better. This is when air side is common in a common plenum. If you have separated throttles and air inlet and no connection on air side, it becomes much more like the 360-degree engine. Some people might think that the noise or the sound maybe of these uneven firing engines do create some happiness, so I will not comment on that. But engine control-wise, when you have engines, cylinders, operating at different volumetric efficiencies, you need to have more competence built in order to fuel the cylinders differently, so the air-fuel ratio becomes the same on each cylinder. Okay, cylinder interaction on exhaust side most of the time is bad news. You get disturbances from other cylinders which you could just try to get rid of. On the air side, there are some situations which could be a benefit for you, and one of those examples is the traditional 4-cylinder engine. We recognize the cylinders here, 1, 2, 3, 4. They end up in a common plenum. It's a mildly tuned engine with not too big valve overlap, so we have a common throttle plate. The blue pipe here, upstream the throttle, is called secondary pipe. The yellow one is primary pipes, known from the single cylinder course. We jump the plenum, we come to the secondary pipe. Most engines have an airbox and a filter box, and maybe also a little bit of a snorkel going to the atmosphere, and that is called torture pipe. The 4 primary pipes, in the primary pipes they merge in the plenum and they create a common pressure pattern which is I try to sketch here. The amplitude of the pressure waves here are much lower than in the inlet primary pipe, but they do exist. And together they excite or send out pressure waves to the filter box, which are reflected and coming back as compression waves, moving into the engine again. So in the same way as the inlet primary pipes are capable of generating compression waves when the inlet valve is closing, we can obtain the same thing from the secondary pipe on an inline 4-cylinder engine. Looking at the volumetric efficiency curve versus engine speed, we recognize the traditional peak in volumetric efficiency, which comes from the inlet primary pipe tunings. But what is new is that we have another crest further down in engine speed, and that resonance or assistance is coming from the secondary pipe. There is also a little hit here because of the 30 pipe, but the amplitude is much less. To balance the peak between the primary pipe and the secondary pipe, the medicine is to change the volume in the plenum. So small compact plenums, especially for old carburetor engines, have a tendency to give priority to the secondary pipe, and this peak will jump up to the expense of the primary pipe, which will go down. In a competition engine where this is just not interesting, you don't want a plenum box, you want to give priority to the primary support, and therefore on racing engines, either the plenum box is very big or being not existing. Different inline 4-stroke engines with a common plenum and even firing between 1 to 6 cylinders have been identified with the average volumetric efficiency, not for each cylinder, but one delivery ratio curve for each engine with one specific number of cylinders. And they create a certain signature. So typically, a 2 3-cylinder engine will have some resonance from the secondary pipe happening somewhere around 2000 RPM at a secondary pipe length of about 500 millimeters. The 4-cylinder engine, which starts to have some interaction between the cylinders, which the 2 and 3-cylinder engines don't have in neither on the exhaust side or the inlet side. They create a very specific signature, so they will excite the secondary inlet pipe at a bit lower engine speed, in this case 1500 RPM. When we jump from 4-cylinder up to 5-cylinder, 6 or even up, the resonance or the assistance from the secondary pipe diminish and goes away completely, because the excitation of the plenum box is no longer happening when you go from 4-cylinder up to 5 cylinders, because there is too much short circuiting between the cylinder faces. Charging system makes it very necessary to connect cylinders with each other, both on exhaust side and on air side, especially if we're talking turbochargers. Turbochargers needs to be fed by as hot exhaust gases as possible, and also having availability to the pressure unsteadiness, which also helps to drive the turbine. So for turbochargers and turbines, we like them to be close to the engine. If we have a cylinder number or firing order with a lot of interactions on the exhaust side, we should be a little bit cautious with turbocharging. Not giving it up, but one solution might be to add more than one turbocharger to divide different cylinders from each other to avoid the interaction. In some cases, for boxer engines and V engines, which have a tendency to distribute exhaust pipes all over the place, the heat losses will be enormous with only one turbochargers, so also an argument for having multiple turbochargers. There are also engines which might be better off with superchargers than turbochargers, because keeping the number of turbochargers down, and I will come back to that later. Superchargers, they will leave the exhaust side completely free, so they don't make the interaction between the cylinders significantly worse. But on the other hand, especially with throttle plates sitting upstream the compressor, the throttle volume have a tendency to become very big. So you like to push the compressor closer to the engine, and there are installation arguments also, which might be even more important. So if you have interactions on the air side for your engine, because maybe of uneven firing fire orders, you should at least be aware of that as a challenge. The V8 engine is very often supercharged with good results. They are uneven firing on each bank, so we have this risk. But on the other hand, the installation opportunities for a supercharger in the deep V created by the 90-degree bank angle is of course very tempting and good for supercharging. I'd like to thank you very much for attending this very long presentation for multi-cylinder engines. And if you're interested to read a little bit more or contact me, you have the information here. Thank you for your kind attention.